Hi everyone. In this lesson, we'll explore K-means clustering, an unsupervised learning method based on distance-based grouping. Let's dive in. Unsupervised learning is a branch of machine learning that focuses on discovering the structure of the problem that generates the data, including hidden patterns, groups, or features. Using in-labeled data, it is generally examined under three main categories: clustering, dimensionality reduction, and association rules. Let's take a brief look at these three titles. The first approach in unsupervised learning is clustering, which is used to group data with similar characteristics. The most common method is the K-means algorithm. For instance, it can be applied to customer segmentation or developing marketing strategies. Imagine an e-commerce company with demographic data such as age, income level, and shopping frequency, along with customers' purchase histories. Using the K-means algorithm, these customers can be grouped into clusters, which can then be leveraged to create personalized marketing strategies. For example, luxury products could be offered to Cluster 1, while discount campaigns could be targeted at Cluster 3. The second topic is dimensionality reduction, a technique used to condense high-dimensional data while preserving its essential features. The most widely used method for this purpose is principal component analysis. PCA identifies the key sources of variance in the data and simplifies it accordingly. This method is particularly valuable in image compression, noise reduction, and data visualization. For instance, consider developing a face recognition system that requires processing large volumes of high-resolution images. Each image contains numerous pixels, resulting in a substantial data size. PCA helps by analyzing this high-dimensional data and extracting principal components that capture the most significant variations between faces. These components retain the crucial features of the original images, allowing the face recognition algorithm to operate more efficiently. Consequently, this leads to faster data processing and reduced memory usage. The third approach is association rules. The approach is utilized to discover relationships and patterns within data. The most popular algorithm is a priori. The algorithm analyzes item combinations in the data and identifies meaningful relationships using metrics like support, confidence, and lift. It is commonly applied in market basket analysis. For example, it can identify which products are frequently purchased together through market basket analysis. The example of diapers and beer is notable for its memorability. According to the legend, data analysis revealed that young fathers tended to buy beer while purchasing diapers. This finding led retailers to place the two products side by side, resulting in increased sales. In this tutorial, we will focus on the K-means algorithm. Now let's look at the steps of the algorithm. In the first step of the K-means algorithm, K-random center points are selected. These centers serve as the initial points for the clusters. In the second step, each data point is assigned to the nearest center. This means each data point is grouped into the cluster associated with the closest center. Next, the centers for each cluster are updated by calculating the mean of the data points within that cluster. Then, steps 2 and 3 are repeated until convergence is achieved. The operations performed up to this point are referred to as an iteration step. Two criteria are generally used for convergence: no change in the cost function and reaching the maximum number of iterations. Let's examine the K-means algorithm step by step on an example. First, we need a dataset to cluster. Here you see the two-dimensional data points we artificially generated. No point in this data appears different from the other. The K-means algorithm does not aim to find how many clusters there are in these already labeled points. Therefore, The user gives it the number of clusters. Let's say k equals 3. The k-means algorithm is a very effective method to divide the dataset into homogeneous subgroups. However, it should be noted that the parameter k must be determined in advance and that the initial centers may affect the results. Therefore, this algorithm should be repeated several times with different initial points. Let's say that we have determined 3 different cluster center positions for k equals 3 with the random number generator as shown on the screen. At this stage, we now group the points we have according to their distances to the 3 randomly determined cluster centers. Here, we chose green for the data points close to the K1 center, red for K2 and its members, and purple for K3. Thus, it is easy to understand which data point belongs to which cluster. Although the most used criterion in distance calculations is Euclidean, Manhattan distance is also frequently used for ease of calculation. At this point, the cost function, denoted as J, can now be used to assess the quality of the clustering. A smaller value of this function indicates better clustering. Therefore, this cost value is also useful for evaluating the clustering process across different k-values. But here, we calculate the cost function to check how much the J value changes from one iteration to the next. We now have a clustered dataset, albeit temporarily. Here, we need to update the cluster centers by taking the average of the data points that are members of it. When the arithmetic average of all the green data points is taken, the center K1 suddenly makes a big jump. Similarly, K2 moves for the red data points and K3 moves for the purple data points. With these location updates of cluster centers, an iteration is completed. Now let's prepare for the new iteration. Now that the cluster centers have been updated, we must regroup the data points according to the new location of the cluster centers. When regrouping is done according to the distance to the nearest cluster center, it is possible to see that some data points switch sides. Here, the 2 marked data points have changed their cluster membership. You can confirm this by rewinding the video. As shown in the example, some data points may switch clusters with each iteration of the k-means algorithm. This change is normal early in the clustering process. However, if it continues in later iterations, it could indicate a potential issue. There are several reasons for this behavior and its possible effects. The first reason relates to the proximity of data points to cluster boundaries. If a data point lies near the boundary between 2 clusters, even a small shift can cause it to be reassigned to a different cluster, leading to instability in the algorithm's iterations. The second, k-means is sensitive to the initial points of the cluster centers, and different starting points can lead the algorithm to produce different clusters. The third reason concerns non-spherical clusters. K-means assumes that data points form spherical clusters. If the clusters in the dataset to process are not spherical, some points may be reassigned to different clusters with each run of the algorithm. At this point, the quality of the clustering is recalculated using the cost function and the found value is compared with the previous cost. If there is no change, the algorithm is stopped. However, it is not reasonable to always look for no change in the cost function in clustering. Therefore, a very small threshold value, such as 0.001, is used to represent no change. If the change in cost falls below this specified threshold, the centers are considered stable, and the algorithm is stopped. However, in some datasets, no change in the cost function may not be achieved due to poor initial values. In this case, the algorithm can enter a loop forever. To prevent this situation, a maximum iteration limit, such as 100, is often set. If convergence is not achieved and the maximum iteration is not reached, all data points are reassigned to the nearest cluster center and the calculation continues. Since mathematics is considered the common language of the entire universe, it is important to be able to read mathematical formulas. At this point, stop the video and try to interpret what the cost function on the screen means. Here, the value xm represents all data points belonging to cluster capital Ci, while the value lowercase ci represents the center point of the cluster capital Ci. Let's examine this together. It is clear from the screen that the cost function involves two series of addition operations. The inner addition calculates the total within cluster costs for each cluster separately. The outer total then sums these within cluster costs to compute the overall cost of the clustering process. Squaring the distances in the inner expression helps to eliminate negative values and amplifies the effect of distance changes. You can solidify your understanding by coding these concepts yourself. The first ideas of the k-means method emerged in the 1950s with an approach that was founded by different researchers. However, it is accepted that the work that brought it to its current fame was done by James B. McQueen in 1965 and 1967. The algorithm is so susceptible to being manipulated that dozens or even hundreds of variations have been produced. In this form, it is also seen as the Play-Doh of data science. The fact that an algorithm has such a great reputation for such a long time requires us to look at it in more detail. Let's start with the advantages first. 1. K-means is straightforward and easy to understand. The algorithm involves calculating the centroids and assigning data points to the nearest centroid, making it simple to implement and interpret. 2. K-means is generally fast, especially with large datasets. It efficiently computes distances and updates centroids in each iteration, making it suitable for large-scale clustering tasks. 3. K-means is memory efficient, as it primarily requires storage for centroids and data points. This efficiency is beneficial when dealing with large datasets. 4. The algorithm quickly adapts to different datasets. By varying the number of clusters, it can be applied to various data structures and distributions. 5. K-means usually involves only a few parameters, such as the number of clusters. This simplicity makes it easier to configure and apply to different problems. 6. K-means can be used across a wide range of datasets. It works well when there are clear distinctions between clusters. No algorithm is perfect, even k-means. Therefore, when learning each algorithm, we should know its advantages and disadvantages, so we know where and how to use it and where it will work well and badly. This also affects our interpretations. Now it is time to learn its disadvantages. 1. K-means requires the number of clusters to be specified in advance. Determining the optimal K can be challenging and may require additional methods or trials. To handle this problem, you can use methods to determine the optimal number of clusters, such as the elbow method or silhouette analysis. These techniques provide metrics to help identify the most suitable value for K. 2. The algorithm is sensitive to the initial selection of centroids. Poor initial choices can lead to suboptimal clustering results or local minima, affecting the overall outcome. Running the algorithm multiple times with different initializations and selecting the best result can help. 3. K-means assumes clusters are roughly spherical and of similar size. It may struggle with clusters of varying shapes and densities, potentially leading to poor clustering performance. To overcome, consider alternative clustering algorithms such as DBSCAN or mean shift for datasets with clusters of complex shapes. These methods are better suited for identifying clusters of varying shapes and densities. 4. K-means is sensitive to outliers, which can skew the centroids and impact the clustering results. Outliers may lead to inaccurate cluster assignments. Reduce sensitivity to outliers by performing pre-processing steps to remove or limit outliers. 5. The algorithm assumes that clusters are approximately evenly distributed. This assumption may not hold true for all datasets, leading to less accurate clustering. Since K-means assumes that clusters are approximately of equal size, other clustering techniques like Gaussian mixture models, GMM, can be used. GMMs can handle clusters of different sizes and shapes more effectively. 6. K-means can converge to local minima rather than the global optimum. This can result in different clustering outcomes based on the initial centroids and may not always find the best clustering solution. Repeating is easy and cheap solution. Address convergence issues by running the algorithm multiple times with different initial centroids and selecting the best outcome. Now we will see an example of manual calculation. The question asks us to find how the cluster centers change with one iteration of calculations for the given dataset on the screen. At this point, I suggest you stop the video and do the calculations manually. Then you can continue and watch the solution. We can skip the first step of the K-means algorithm for this question since it is given that K equals 2. And the initial positions of the two cluster centers are provided. Therefore, we can begin directly by calculating which cluster center each data point is closest to. Since the Manhattan distance is specified, our task becomes simpler. On the screen, the distances to both cluster centers are calculated for each of the 4 points in the dataset. Based on these calculations, the first, third, and fourth points are closest to C1, while only the second data point is closest to C2. According to the next step of the algorithm, the cluster centers are updated by averaging the data points within each cluster. For the new position of C1, the average of the 3 closest data points is calculated, resulting in -1/3, 8/3. Similarly, C2 shifts to its new position at 5, 4, aligning with its sole data point. With this calculation we have completed the lesson. Thanks for watching. We recommend that you attend class for in-class activities.